If we substitute this spinor there, you can see that it is E over C 0 0 0 0 E over C 0 0 0 0, this minus E over C 0 0 0 0 minus E over C. Times the U1 spinor. U1 spinor is 1 0 0 0, and that is equal to m naught C 1 0 0 0. So from this equation you can simply find this energy associated with the U1 spinor. So on open this, you can see that this gives this E by C, all remaining are 0, so E over C is equal to m naught C 0 0 0. So this implies E by C is equal to m naught C for the U1 spinor, and that implies E is equal to m naught C square for the U1 spinor. So you simply see that the energy associated with the U1 spinor is positive. So similarly, let me analyze the U2 spinor. In rest frame, we can write the U2 spinor as as 0, this U2 spinor 0 1 0 0. So if we substitute this U2 spinor here 0 1, that will also 0 1, that will give this E by C and m naught C in this second element. So we get 0 here, E by C here, 0 here, m naught C here, and that also give this E by C is equal to m naught C, and that gives E is equal to m naught C square. So we can say that the U1 and the U2 spinors are positive energy solutions of the Dirac equation. Let me analyze the U3 and U4 spinors. We know that the U3 spinor is CPZ over E minus m naught C square C Px plus IPy over E minus m naught C square 1 0. So in rest frame we can write, we know that this Pz, Px, Py are all 0. So in rest frame we can write U3 spinor as this Pz is 0, Px and Py's are 0, the remaining is 1 0. So this U3 on the Dirac equation on rest frame gives 0 0 1 0 0 0 1 0, and that gives this projects this minus E by C, this minus E by C outside. This case is different from the previous case because this one here projects this minus E by C, this minus E by C outside. So that's the main difference here. So here this minus E by C, minus E by C 0 m naught C, and here this minus E by C is equal to m naught C. Minus E by C is equal to m naught C. That gives this E is equal to minus m naught C square. E is equal to minus m naught C square. So what we see is the energy associated with the U3 solution is negative. So let me ask you, do the negative energy particles exist in nature, or what is the physical significance of these negative energy solutions? We will discuss it later after a few minutes. Let me analyze the U4 spinor too. We can write the U4 spinor in H frame as 0 1, and here it is 0 1, and this one projects this minus E by C 0 1, minus E upon C 0 m naught C, and that gives the same result as U3 spinor does. Minus E by C is equal to m naught C, so that gives E is equal to minus m naught C square. So we get the energy associated with the U4 spinor is also negative. From the dot product of the 4 momentum, we know that E by C whole square minus P square is equal to m naught C whole square. This gives E square is equal to m naught square. This E comes here, gives E raised to 4 plus P square C square, and this implies E is equal to plus or minus root of P square C square plus m naught square C to the power 4. So if we put this momentum P is 0, we get plus or minus m naught C square, and this is exactly the same as the rest frame solutions. So from the analogy, we can say that this E is the solution for moving particles. So this E is equal to plus root of P square C square plus m naught square C raised to 4 associated with the U1 and U2 spinors for moving particles, and this minus root of P square C square plus m naught square C raised to 4 associated with U3 and U4 spinors for the moving particles. Now we have the solutions for the Dirac equation, that is psi of P is equal to e to the power minus I over h cross x mu p mu u of p, psi I of p u I of p. So there are 4 solutions, 2 correspond to positive energy and 2 correspond to negative energy. We will see the significance of negative energy later. In fact, this solution is not normalized because psi I of p diagon times psi I of p not equal to 1. So we need to normalize these solutions. For that, let me add a normalization constant n I here, and let us find the value of this ni. We will see that these ni's, that is n1, n2, n3, n4, all are equal. Let us first normalize psi 1 and find the value of n1. So we have the condition that psi 1 diagon psi is equal to 1. This implies the psi 1 diagon is n1 diagon, this exponential diagon times u1 diagon. So n1 diagon is actually n1, and the complex conjugate of this exponential part is e to the power I by h cross x mu p mu, and the complex conjugate of u1 is u1 diagon times the psi 1. The psi 1 is n1 is actually n1 e to the power minus I over h cross x mu p mu u1. So you can simply see that these two exponential part cancels to 1. So this is actually equal to n1 square times u1 diagon times u, and here the condition tells this should be equal to 1. This should be equal to 1 because due to this condition. From this equation we can simply find the value of n1. For doing that, let us first find u1 diagon u. We know that u is u1 diagon u. So let us first write u1. We know that u1 is 1 0 c p z over e plus m naught c square c px plus ipy over e plus m naught c square. In fact, this is actually a matrix. So its diagon means Hermitian conjugate. What is actually Hermitian conjugate? The transposed complex conjugate of the matrix. So its transpose is 1 0 c p z e plus m naught c square, and it's also the transpose complex conjugate of the matrix. So its complex conjugate is c px minus ipy. So here it is c px minus ipy over e plus m naught c square. This gives 1 plus 0 times 0 0, and this cpz times cpz over e plus m naught c square is c square pz square over e plus m naught c square whole square. And also you can see that px minus ipy times px plus ipy is actually px square plus py square, because you know that a minus ib times a plus ib is a square plus b square. So from this we can write c square pz square plus py square plus px square over e plus m naught c whole square. This is actually the square of the magnitude of the three-dimensional momentum. So we can write u tangent u. So we can write this gives u1 tangent u is equal to 1 plus c square magnitude of the 3 momentum square over e plus m naught c square whole square. From the dot product of the 4 momentum, we already have e square minus c square magnitude of 3 momentum whole square is equal to m naught square c to the power 4. So on substituting the value of c square p square to here gives u tangent u1 tangent u is equal to 1 plus, that is c square p square is equal to e square minus m naught square c to the power 4 over e plus m naught c square whole square. This is actually equal to 1 plus e plus m naught c square times e minus m naught c square over e plus m naught c square whole square. You can simply cancel 1 e plus m naught c square from the numerator and also 1 e plus m naught c square from the denominator. That gives this. E minus m naught c square. On taking this denominator to the numerator gives e plus m naught c square plus e minus m naught c square over e plus m naught c square. This plus m naught c square and this minus m naught c square cancels and this e and e adds up. So this is actually two e. Now we have the value of u1 tangent u, which is equal to 2e over e plus m naught c square, and we know that n1 square u1 tangent u should be equal to 1, and this is our normalization condition. So from this equation you can simply see that n1 square is equal to 1 over u1 tangent u. So that gives n1 is equal to root of 1 over u1 tangent u. From this equation you can simply see that 1 over u1 tangent u is 1 over u1 tangent u is equal to e plus m naught c square over 2e. That is actually equal to 1 by 2 1 plus m naught c square over E. So root of 1 over u1 diagonal u is root of this. Let me take this root to the power. So that is whole raised to 1 over 1. This is the normalization constant n1. You can simply see that n1 equals n2. n2 is the normalization constant corresponding to u2 spinor. And also for a u1 and u2, this E is positive. That is, this E is always greater than 0. For u3 and u4 spinors, the value of normalization constant is little bit different because the energy is negative for u3 and u4 spinors. But you see that in fact these 4 normalization constants are same. But it's little tricky in the case of u3 and u4 spinors. You know that for u3 spinor, the first element is Cpz over E minus m naught c square. Second element is C px. Here this complex conjugate comes here, px minus ipy over E minus m naught c square 1 0. Here Cpz over E minus m naught c square. Second element is C px plus ipy over E minus m naught c square 1 0. On multiplying these matrices, you can see that u3 diagonal u3 is equal to 1 plus c square pz square py square px square divided by E minus m naught c square whole square. So we replace these px square py square plus pz square with the e square minus m naught square c raised to 4. But the difference is here the sign is minus. So that gives, here the sign is minus. This equation is actually E minus m naught c square times E plus m naught c square. So E minus m naught c square from the numerator cancels with the 1 E minus m naught c square from the denominator. That gives E minus m naught c square. In the numerator we get E plus m naught c square. On taking this denominator to the numerator, cancels m naught c square with minus m naught c square and adds both e's. That gives 2e divided by, here it is E minus m naught c square. So this is actually u3 diagonal times u3. So 1 by u3 diagonal times u3 gives E minus m naught c square over 2e minus m naught c square over E, and this E is actually negative. E is less than 0. You can simply see the difference here. This normalization constant is different with a minus sign as compared to the normalization constants in the case of u1 and u2 spinors. But the presence of this minus sign is cancelled by the presence of these negative energies. This energy is always negative, so you can simply write this E as magnitude of E a minus outside. So that is similar to the case of, you can simply write minus 2 as magnitude of minus 2 times a minus. Magnitude of minus 2 is actually what? That is actually 2 times this minus minus. So that is, both are same. So we just write the negative energies as magnitude of the energy times the minus outside. So these two minuses cancels and gives a plus here. So in general, you can write the normalization constant for U1, U2 and U3 and U4 spinets as this. So in general, you can write the normalization constant for all spinets as 1 over 2 1 plus m naught c square over magnitude of energy times, not times, raised to 1 by 2. And here the energy can be negative as well as positive. There is another type of normalization scheme also, in which U diagon U is equal to mod E over m naught c square. You can see this normalization scheme in J.J. Sakurai's Advanced Quantum Mechanics book. Let me explain the physical significance of negative energy solutions. There are basically two types of interpretations. One is Dirac theory and the other one is Feynman-Stackelberg interpretation. Let me first explain Dirac theory. According to this theory, the negative energy states are completely filled in accordance with the Pauli's exclusion principle. Let this be the negative energy states, and this particular state corresponds to the energy minus m naught c square. And this be the state of zero energy, and this be the states of positive energy, and this particular state correspond to the energy m naught c square. So in accordance with the Pauli's exclusion principle, these negative energy states are all completely filled. So due to Pauli's exclusion principle, we can only accommodate 2 electrons in a particular state. So these all states are completely filled. And these completely filled negative energy states corresponds to vacuum. VACUUM. So according to Dirac theory, the vacuum consists of negative energy states, and all that negative energy states are completely filled. For the case of electrons, these all negative energy states are completely filled with electrons. By quantum laws, it is possible to excite the electrons in this negative energy state to these positive energy states by supplying some amount of energy. How can we supply some amount of energy to these electrons in these negative energy states? We can use gamma rays. So it is possible for gamma rays to excite electrons in this negative energy state to the positive energy states, leaving a vacancy in the old position. Now the electron here is at the positive energy state, and this vacancy or hole is called antiparticle. From the law of charge conservation, we can easily see that before and after the excitation, the charge should be 0. So the charge of this electron plus this particle, let me denote it by E plus, is equal to 0. We know that the charge of electron is negative, so the charge of this antiparticle or this vacancy or this hole should be positive. And the electrons in this negative energy states have negative energy. So this vacancy or hole in this negative energy state have positive energy. These have positive energy. So we see that the vacancy or hole corresponds to the electron in the vacuum have positive charge and also have positive energy. And we named it as positron, the antiparticle of electron. And this particular process is called pair production because a gamma ray is converted to an electron and a positron. And remember that for conserving the momentum, we need the presence of an additional nuclei for the happening of this electron-positron pair creation. The reverse of this process is also possible, that is an electron and a positron annihilate to produce some energy or gamma ray. That is, an electron here jumps to this gap or hole in this direction, lead to the production of a gamma ray, and this is called electron-positron annihilation. The second interpretation for negative energy states is Feynman-Stackelberg interpretation. Let me explain it a bit. We already know that the free particle solution of the Dirac equation is psi I of p is equal to e to the power minus I over h cross x mu p mu ui of p. To talk about the negative energy states, we only have the need to take the energy part of this expression. So what's the energy part of this expression? It is actually e to the power minus I over h cross, the time part is ct, and the time part of the form momentum vector is e over c times ui of p. So this c cancels and this gives e to the power minus I over h cross et times ui of p. In fact, this expression is equivalent to e to the power minus I over h cross minus e times minus t, because these two minuses multiply and cancels to 1. Let me analyze this expression first. For negative energies, this E is actually negative. E is less than 0. And according to this interpretation, for this E less than 0 or E for the case of negative energies, this time running backward or this T is also negative. Let me draw a pictorial representation of this. That is, the negative energy states corresponds to the particles travels backward in time. This is a t-axis. This is a particle travels backward in time. But coming to here, this minus E is positive. Let me denote this minus E by some E dash, and this E dash is positive. And this is minus T. So this minus T in effective, it is running forward. T is greater than 0. Minus T is greater than 0. So let me denote it by some T dash, it is greater than 0. So this equation tells a positive energy antiparticle that travels forwards in time. So what this equivalence says is a negative energy particle that travels backwards in time is equivalent to a positive energy antiparticle that travels forwards in time. Let me pictorially represent this here, and this is actually equal to the arrow is in the opposite direction. This corresponds to a negative energy particle travels backwards in time because arrow is negative and T in this direction is decreasing, and this corresponds to a positive energy antiparticle that travels forwards in time. Look at the arrow, it is in the forward direction of the time. In fact, this arrow convention given by Feynman-Stackelberg interpretation is used in drawing Feynman diagrams. Let me draw a Feynman diagram for you. Let me draw the Feynman diagram for this case. We can draw it as a gamma ray coming here, and it is pair produced into an electron and a positron. This is electron this is a positron. So using that arrow convention, this is an electron and this is the time direction. This is the time direction. So this positron can be represented by a particle or electron travels backwards in time. And this is the electron and this is the positron. And this positron travels forwards in time. So this can be equivalent to an electron that travels backwards in time. There are some advanced steps that we can take from this Dirac equation. One is called the Dirac-Euler equation. Dirac-Euler equation is a Dirac equation that is formulated in Clifford space. There are a lot of mysteries hide inside Dirac-Euler equation. And using this Dirac-Euler equation, I think we can solve some mysteries in this universe, like how the Big Bang happened, etc. And also, this Dirac equation is not the ultimate theory that combines quantum mechanics with special theory of relativity, because in fact these negative energy solutions are a deficiency of the Dirac equation. So the ultimate theory that combines quantum mechanics with special theory of relativity is quantum field theory, and we don't have quantum field theory in our syllabus. So if you like to study quantum field theory by yourself, please write to me. I will give you enough suggestions to study quantum field theory by yourself. Thank you.